Good. Yeah, I see you recording. Okay. So now we have recording on and officially we can start. So just see what the chat was. Aliba is saying the lecture will be public on YouTube. I don't know, anybody can see that, that's fine. I have no problem. I like large crowd. Okay. So let's get going. Here we go. You like full screen, right? So I do full screen. Here we go. So good afternoon. And we basically finished the equations and both integral and differential form. Last week was kind of difficult, abstract, and many of you were wondering what kind of course this is going to be. So from now on, it's going to be quite easy, and I expect you to understand what we're doing. We still have some math a little bit, but very, very minor compared to what we did last week. However, we do need those equations, so you'll see how it will evolve during the semester. So here it says that the simple case is when actually fluid is not moving. So if fluid is not moving, they have hydrostatics. And hydrostatic is still covered by the Navier-Stokes equation. So we just want to show that even that simple case is covered. It's kind of coming out of the same equation. And then with hydrostatics, we're going to cover like a few issues. I put here 4 cases. I think I just listed 3 of them. We'll figure it out. Apart from just discussing hydrostatics, there is some objective here. We're trying to learn about how the pressure is affected by gravity. That's very simple introduction, equations that you know. And then we do pressure in accelerating fluid. Again, we'll have to explain what it is because the fluid is not moving. So it's like you have a fish aquarium and the fish is in there and then you accelerate, but the fluid is not moving. So the whole thing is moving, and you can compare that to gravity. Gravity is also acceleration, but to the negative directions. And then we do buoyancy. Turns out that those equations will come up with the same conclusion that Archimedes came out way back 2,000 years ago. Okay, so I say again, last week was abstract, and don't worry, from now on, you should be able to understand everything, and it's going to go well. Now, usually I go over what we did before very quickly, so let's do that again. So we did the integral form of the equations, and basically it's in the control volume. Usually we would like to put the object of interest in the control volume. And the statement of the control volume is that whatever goes in goes out. If there's a difference, then there's an accumulation. But the mass overall is conserved. Okay, so that's, we showed that. Momentum is the same thing. Whatever goes in comes out. If there's a difference, then there's accumulation inside that little control volume. But then Newton said that MA equals sigma F. So now we have to figure out what are the forces. And we discussed that there are body forces like gravity. This is the only one we're going to deal with. It could be magnetic forces and things like that. And then here in this particular equation, if I put the cursor on, we actually put the shear as well. And we separated the pure shear from the pressure. It looks very good, but at the end of the day, we used only the one-dimensional model. And we're going to continue in the next chapter, the one-dimensional flow, which is pretty good for predicting some simple effect and some global understanding of, say, thrust and forces and things like that. So in this particular case, we're looking at a control volume which is surrounding, let me get a pen. control volume, which is surrounding the, working, okay, for surrounding this volume. And we just investigated what goes in, what goes on. We looked at the coordinate system. We looked at the surface, that the normal is always pointing outside of the surface. And we looked at steady state and assumed that the shear is actually represented by some force which is acting on that control volume. And we concluded that that equation, which we had in the previous page, simplifies to that. And when we applied the one-dimensional model, we ended up with the continuity or conservation of momentum. So it's incompressible, therefore whatever goes in or whatever goes in goes out. And the force, and that one you have to remember, and it's very easy to remember, by the way. The force in a situation like that is the momentum coming out, this one, minus the momentum coming in or going in, this one going in here. And then the pressure. If the pressure here is higher than out, then there's a pressure term. If the pressure is higher here, then there's a negative pressure term. Okay, that's a very, very simple. And then we had some examples, and we'll do more on that. We'll do more on that. But again, this is very, very simple. I want you to be able to do examples with these equations for sure. Okay. All right. So then we went into the develop the differential form. That was a bit more complicated, and we kept on going. But what would I like you to see or understand? Let me just go back to the next slide and come back. So it is the same equation, but in vector form. So what we have here is acceleration. Let me get the pen. So acceleration in vector form equal body forces, pressure, shear. This is the shear that we discussed, very simple. And that one is the shear due to compression, Now, if the fluid is incompressible, no compression, then we lose that term. Okay, so then because the delta Q is 0, and we end up with this equation, which is the incompressible Navier-Stokes equation. Okay, and then if it's also inviscid, which we would like to throw away this term, then we end up with this, which is called the Euler equation. That was the first equation which was developed by Euler, and then a viscosity was added later on. So now I go back to the previous one. Yeah.
Code now. The code.
You asking a question, or are you talking to the neighbor? No question. Okay. So now this equation, this one, which is the most complicated one, it was actually shown in here. So we substituted everything. And this is the full Navier-Stokes equation. And I actually didn't put here the continuity because it was also complicated, but I showed it before. And look, it's a pretty unpleasant to look at that. Partial differential equations, you did not study anything in math to do that. Has no solution, only numerically. Nowadays we can solve that. And then what's interesting is the boundary condition, because this is velocity square, actually, second derivative here, which is the terms that we discussed with the shear. And we need to supply boundary condition of solid forces, which means that velocity normal is 0. And also remember the no-slip boundary condition. So the tangential to, let's say, y and x are going to be also. So there's going to be 3 velocity components 0 at the surface. So this is just so you don't get scared from the equation, you know what they are. Usually we will refer, if you're trying to simplify those equations, to that version, either the Euler version or this version. And I hope I have it the next slide, yes. So if we have, oh, I put here Euler, but it's really, it could be also the incompressible flow. So remember we have rho, u, d, rho, dx, and things like that. if the fluid is incompressible, the box comes to that. So what it means is that the velocity, the x direction, if there's a change, it must be compensated by other directions because the fluid inside the box is conserved. It's not going to change. It's incompressible. As an example, I put here a body force because we put F. What is body force? I kept on saying G. So our coordinate system usually Z is going to point up. Therefore, the body force is going to be 0x, 0y, and then minus G to the Z direction. If I put it in the inviscid Navier-Stokes equation, sorry, to incompressible Navier-Stokes equation, we end up with this. Now, I would like to keep that set, including this one, as some sort of baseline which is providing us the roadmap for the rest of the semester. Okay, so this is very simple. I did discuss the acceleration term. However, we mostly assume that it's unsteady, so we're not going to use these terms. So we're going to end up with this. Okay, so this is acceleration in steady state, and I explained that it's possible because fluid can accelerate if we turn, say, a pipe. Then we have the pressure term, pressure, pressure, pressure. And then we mentioned the body force is only on the Z direction, okay? And these are the shear. Remember the two sides of the box, we said du dz, for example, if the velocity is today, we discussed this term, okay? We discussed this term and we have the one plate moving and the other one not, and then we had the velocity profile like this, if you recall. We had that one. This is that case, but now we have the box, so therefore we have a derivative between left and right, and therefore we have the second derivative. I explained that previous class. I just want to make sure that we're on the same page and you're going to be okay with that. Okay, so this is kind of refreshing your memory. And okay, so this week we're going to talk about fluid statics. Velocity is not moving. So let's go back to the previous page. So we start with these equations, okay, and but no velocity. So if there's no velocity, there's nothing here. So 0 equals 0. Then we're looking at that side, pretty much nothing there. However, we're going to do a little trick here. These terms remain. There's no velocity, definitely no second derivative, so we lose all that. So what I'm going to do is actually, we're going to say that this was actually A, the acceleration, X, Y, and Z. I would keep that term, but now not the fluid accelerating, but the whole container is accelerating. Okay, so this is the only exception we're going to make. So with that said, and then we said here, Q is equal 0, no velocity. Then the conservation of mass, the first equation which I mentioned says nothing happens. And then I discussed this equation here. Oh, I need the pen, I need the pen, I need the pen. So then I showed you before that equation, but as I said that instead of all this, I'm just going to say rho A, I just multiplied by the rho, the whole equation. So I say rho acceleration. This thing is something, I don't know, left over for somewhere. And then we have the body force, and then we have gradient P. I'm just concerned for a moment because that's supposed to be the vector, I believe. And this is also a vector. So I moved that from a different computer, and I think Microsoft is pulling up a trick on me. Anyway, so we end up with this equation here, which is the one we're going to use. Most of the cases, we don't have A because there's no solid body acceleration. So body force versus pressure, that's what it is. Okay, all right. So now let's just go back to the shear, this one here. There's no motion, so the only components are the X, Y, Y, and Z, which are pressure. So all we have is this one, this, and this one have that one, pressure, and this one have the one, we have this one. However, Pascal stated, and it's true anyway, that the pressure at the point is the same to all directions. So all these pressures are the same. So this is the shear matrix for this particular case, and it's very, very simple. Here I'm just saying that note that we left the acceleration term for future use. Okay, so one more time, Navier-Stokes equations. We mentioned the fluid is not moving, and we ended up with this term only. I put the rho A just for future, but at the end of the day, this is the equation we're dealing. First, pressure versus body force. Okay, let's move on. So let's see how this thing works. Question?
Yeah, I have a question. Are these the slides for the day?
Yeah.
Because, okay, what you posted wasn't the slides. You just posted chapter 3.
It's a summary of what I'm going to talk today. I'm not posting the, if you look at the previous lectures, I'm posting a summary of, and the summary will come after I finish the lecture. These are my slides which I prepared for the course. Actually, I prepared them yesterday. So
yeah, I thought that you said that if I emailed you beforehand, you would post them for us to use.
You want the slides to be posted?
Yeah, so we can write on.
Okay, we can do that as well. Okay, I'll do it next time. Again, your responsibility to send me an email that morning.
Okay, I'll send it to you in the morning. Yeah, last class you told me to send it to you right before class, so that's what I did.
No, not before class. I need time to go over. My problem is that I prepared all these lectures on an older computer, and now, but the older computer doesn't have internet and all that, and so now I have to move the information, the pages, have to edit them on the old computer, bring that here to the new computer.
I understand. I understand, Professor. It just makes it easier for me, and I know some other students were commenting last class that they would like that too. So.
Okay, we'll do that. Okay.
All right.
Okay, so one more time. So here's it. So I convince you that this is what we're going to work with. This is it. This is it. Now speaking about old computer. In the old computer, I have here a vector, and I have here a vector. And then in this computer, I got that. So you see, here are my problems. I hope that this is the last time I have it. Anyway, so this is the equation. And now let's see what we can do now. So try to remember that equation. So then I'm saying, okay, here's a liquid. Okay, I'm going to this page. And here's example 1. That's example 1, something you already know. Here's a water surface. This is liquid. We're pushing a coordinate system X and Z on the top. And then again, we're going back, the solid body acceleration, this one, which I mentioned, is not there. I just for one case, we're going to use that. And then the body force, F, is going to be minus G. So I go to that equation. Equation 1 says dp dx 0, because 0 left the acceleration. Nothing there on the right-hand side. To the y direction, same story. On the z direction, we have the G. So this is what's left of it. Okay. So derivative, we integrate dp dx. I end up with dp of x is equal constant. Okay. Do the same thing to the y direction, constant. Then I go to the z direction, so I move this to the other side, and we end up p of z integral for rho g dz, and it's equal minus rho gz plus another constant. So I put everything together, constant, all those constant together, and then try to figure out an equation where the pressure varies with the coordinate z. So it's pretty much the same thing. So we need to figure out how much is c. So how about boundary condition? Let's say that at point here at the ground, the pressure is equal PA, which is the atmospheric pressure outside. And assuming that the pressure will increase as we go down, okay, in the water, let's say water. And so Z equals 0, turns out, and then P equal PA. So P of Z equal PA minus rho GZ, and which means that, okay, so one more time. I put here PA, and here this is 0, therefore P at Z equals 0 equals PA equals C. Okay, so that's what it is here. I just did that very quickly. And then resubstitute C, move it to the other side so it looks much better. Actually, I like it PZ minus PA equal, but doesn't matter. So PZ equal PA, which is the constant, minus rho GZ. Okay. Now, usually you talk about depth in the liquid or in the container or in the water pool or something. So instead of Z, we say, or minus Z, we say plus H, okay, as the depth. And then we just get rid of that sign, the minus sign, and then we end up with the pressure. The depth is only going to equal to the pressure outside the boundary plus rho GH, which is the equation, you already know that, right? You know that equation from high school. Just a simple example. Okay, so this is the equation. Whoop. Have to remember to do the pen. So this is the equation we developed, and let me see if it makes sense. So, for example, we have a bunch of bricks, and we're piling them up. And let's say each of them is 1 kilogram, and the base area is 0.2 or 200 centimeters square or something like that. And how much is the pressure? So in that case, we have 1, 2, 3, 4, 5, 6 kilogram per that. So we're going to 300 kilogram force. These are kilogram forces. Actually, 1 kilogram force is 1 times 9.8. So it's 9.8 Newton. Okay. So don't get confused. The kilogram force is multiplied by G. And then for the smaller pile, which has only 3, it's going to be 150. Now, yeah, I say the taller column has larger pressure at the bottom, which of course is logical. Now, what would be the difference between this example and liquid? Let's say you have, you get the pen. Let's say you have the same thing, you have pool, and now you fill it with water. And let's say it's the same density as the brick. So then I go down at the here, and I'm going to have the same pressure as with these bricks. It's going to be P2. Correct? However, here there is no pressure to the side, while here we're going to have a hydrostatic pressure which is going to push to the side as well. So that's the difference between fluid and solid, okay? Because it also applies force to the side. And then the rho GH formula works for solids and for liquid. And that was just very simple. Of course, you know all that. By the way, when I did the examples on the surface tension, I actually used that equation and nobody complained because we didn't prove it, but it's coming from high school, right? Okay, let's go back to Mr. Pascal. Again, 1623, so he was a very short time. He was very young, okay, when he's gone. So he discovered this rho GH formula, but he also said that the pressure is independent of direction and all that. And he showed that example that if you have an open container and then it has different columns, different shape, actually the height of the fluid and the pressure at the bottom is going to be the same, and it's independent of the shape of those branches. That's Pascal, and it's pretty much related to the rho GH rule that we just discussed now. We can continue with this example, and let's say I'm going to block the top. Do I have a pen? Here's the pen. Let's say I'm going to block the top here. And then we're going to add another tube with an H. So what is going to be the pressure in this area? The pressure in this area is going to be equal to the pressure at that section, which is going to be rho GH1. Here it is. Make sense? And what's going to be pressure here? It's going to be equal to H. So it's going to be equal to rho GH and the whole depth. Again, these are Pascal observations, and it is in line with the formula that we just repeated. Okay, so very, very simple. Again, you all know that. I did not discover anything. And this just serves that even the very simple cases are originating from the Fourier-Stokes equations. Okay, so that's the example. Let's continue with a little bit more. Now, when discussing hydrostatics, then, and of course he said the pressure is isotropic, which means that it goes to, at certain points, it's the same direction. And some people refer to that case as the hydraulic jack as well. And we assume that there is a small piston and there's a large piston. And we're trying to lift the vehicle. And then we're thinking that the fluid level is the same, so the rho GH effect is very small. So basically we can claim that the pressure is pretty uniform in that inside the liquid. Or the rho GH factor versus the total pressure is not very, is insignificant. So effective gravity is small, that's what I'm saying. So if the pressure inside is fixed, then we apply force 1, where we're trying to lift the vehicle. And then the pressure, because of the fact that we're pushing that piston, is going to be, this is the pressure, the force divided by the area of piston number 1. But the pressure is fixed, therefore, the force at 2, which is lifting the vehicle, divided by the area, is also the same. Now, that area has to be larger, and remember that the volume is fixed. So just by looking at this formula, we got the pen, we can figure out the mechanical advantage. Okay, so if this area is 10 times larger than where we're pushing, typically you have some kind of a hinge point, and you have a long handle, and then you push on that piston. Let's say I'm pushing down, and then I create a force here, and then the vehicle actually is being pushed up. Okay, so that's the principle of the hydraulic jet. And then the mechanical advantage depends on the area ratio of the two pistons. Now, you wonder how we gain or we're not gaining. So turns out that overall the volume that you're pushing is fixed. So if the volume is fixed, okay, then the work done is the force times the area, okay, pressure times force is pressure, area, and the height. It doesn't show height, but H1 would be, let's say this would be H2, and probably H1 would be much larger, H1. So at the end of the day, it's the same amount of liquid that we're pushing. And then the work is the pressure times volume, which we will get back to that. But in thermodynamics, pressure times volume is work, right? Work for times distance. Let's say H. It's pressure times area times H, and this is equal to pressure and then volume of the fluid, because AH is the volume of the fluid. Okay, this is thermodynamics, which we're not teaching. All right, so that's the mechanical advantage of using hydraulic jacks. Manometer. Manometer was a device to measure pressure, very popular in the past. Nowadays, we have all those electric gauges, which are electric. But in the past, they used those gauges and with little tubes, and then they attach one side of the tube to, okay, let me get the pen before this thing jumps again. So we take, here is an unknown pressure, it's coming from somewhere, and we have a U-tube, we fill it, the water or the liquid is filled all the way, and then now because the pressure is high, it goes up on the other side, and we're wondering how much is the pressure inside. So we think that the pressure at this point is equal to the pressure at that point, because if we put the coordinate system here, then that will be H. And then how much is the pressure anyway? It's because of the open section. And therefore, the pressure at this point here is going to be rho GH. And we can add the pressure outside. So the pressure inside that container, Px is going to be Pb or Pa plus rho GH. Okay. All right, so that's what it is. Very, very simple. Manometers, anybody, an aerospace student, you can go to the wind tunnel and we have some very old manometers, lots of tubes, and this is how they operate. This is how you measure the pressure. You just hook up this side to a pressure where you want to measure, and then the liquid either goes up, the U-tube is longer, it's much longer, okay, much longer, and it's filled all the way, and then it goes either up and down, and this way you can measure plus minus pressure variations. Okay, that's history. All right, so now let's repeat the same thing in compressible fluid, and let's look at gas, at an ideal gas. Let's say like the air. I will show you that it's kind of close to what happens with the atmosphere, but the problem is the atmosphere has changes in temperature, and that kind of changes the whole thing. But okay, so let's see. So we just want to repeat the same example, but now assuming that the fluid is compressible and it's a gas and it obeys the ideal gas formula. So if you recall, we took the equations. These were the equations. And this is what we left after the Navier-Stokes and substituting the body force as minus G, okay? This is how we did before, okay? So now we integrate dP dx and dP dy, and we end up that the pressure to the X and Y direction is constant, so no change. When we're looking at the vertical direction, the Z direction, we have this, which is the same equation as before. However, now we can go back here. We can here and try to substitute dP dz. Okay, and dP dz is equal minus rho g. But instead of rho, we say P over RT, and that's it. So this is the term. So we can plug in, instead of that, we can plug it in here. Okay, just simple algebra. So now just the integration going to be slightly different because why? We have pressure here and we have pressure here. So that calls for a separation of variables and it calls for logarithm, okay? Anybody who remembers algebra from high school. Okay, so here we go. So the integration is not as before. So we said dp dz minus rho g. I just copied it from them. Then we, instead of rho, we did that one. And then separation of variable, dp over p equal, this is kind of a constant, multiplied by dz. This becomes logarithm by integrating, and this becomes constant and z between the two. So we go between, say, two condition 1 and 2. So this is going to be logarithm p2 over p1 equal this, and z2 minus z1. That's basically the solution. Some people don't like it. Some people use the exponential form. Then p2 over p, so p2 over p1 is equal to this. Or we just multiply p2, or leave p2 and multiply by p1, and we end up with this relation. So this is a logarithmic variation with altitude. How much it is, or how critical it is, this is pressure versus altitude. So it's kind of, let me get that. This is kind of, you have to rotate it a little bit, but it shows that this is the pressure high altitude, and then it, as you go down to sea level, it increases dramatically. It's very close to what we derived over there. The main change in the atmosphere is that the temperature is moving up and down. And if you fly in an airplane, this is kilometer, you go maybe 10, 15,000 kilometers, this is minus. So this is a very cold atmosphere here. Eventually heats up because the particles coming from the sun, but it doesn't have a huge effect. At the end of the day, the shape is kind of logarithmic and it's pretty close to that one. I have here an example just to give you confidence with the algebra. We're doing mathematics, and then we claim that we use metric units. And then how this is work, how would this work? So here's an example. The Empire State Building in New York is like 380-meter high. Okay, and you go up the elevator, your ears are kind of feeling the pressure difference. Let's assume that temperature is constant. At 300, it's like 37 or something degrees Celsius. Very much like what outside today. And let's see how much is the expected pressure. So we take the formula from the previous stage, okay? And it's exponent, and this is G. This is the R, and this is the temperature. And then multiplied by Z2 minus Z1, which is 380, which is the height. And we end up with the pressure ratio 9.5, and that's it. Oh, and here is the R. I'm just defining the R. And that's it. So how much is the pressure difference? The pressure difference is 1 minus 955, which is going to be 4.25% or something like that. If I do, yeah, 4.25%, okay? And 1 atmosphere, we call it 101,325 Newton meter square, which is roughly 10 meters of water in the depth if you dive in the ocean. And it gives us this number, which is Newton meter. So I think it's like 4.5. 10% will be, it's like 43 centimeters in the water. I think it is, I hope I'm right. So you diving in the pool to like half a meter, that's the pressure difference between going up and down the Empire State Building. So it's not super dramatic. Now, if you use the rho GH formula, the simple one, so we say density of the air, rho, this is G, and this is the height, H, assuming constant density for the air, we end up with this, which is not dramatic. We end up a little bit more than the compressible, but still not dramatic. Why? Because we are actually dealing in this graph in this little area here. We're not going much. This graph goes kilometers. So again, that's mainly how to use the algebra. And then also to show that what we did makes sense. And in order to see compressibility effect in the atmosphere, you really have to go to very high altitude. Okay, so that's that one. Again, this is just algebra, that's to show what we're doing. And I think that was a good example just to see how can we play that equation, and then just to show the results. Okay, now let's move on to the next one. Again, we are still in a very, very simple case. And I mentioned solid body acceleration. Now I have a chance to explain it, what I mean by that. So here's a picture. Let me get again the pen before the slide jumps on me. So here's a container. You can call it a fish aquarium or whatever. Don't do it at home, okay? Because then the fish is going to suffer. So the whole thing accelerates forward, and then if we set a coordinate system at the top, okay, as shown, and then we assume that probably the liquid will move to the back. This is kind of, we assume that, but at the same time we have gravity working this way, G, and we call that gravity acceleration. So in reality, there's not much difference between AX and G, okay? So we place the coordinate as shown. Okay, so let's go back to the top. So this was the equation that we used. Some book you use the same thing like this, but let's stick to that version, which is similar. So rho A acceleration on the left-hand side equal to sigma F body force. Now the body force could be G and could be acceleration forward. So we're going to have two of them, and then the pressure, which is the same, okay? And then we're going to demonstrate that for two cases. The linear acceleration, which is this one, and then the steady rotation, when we have a container which is spinning around an axis, and then the fluid goes to the sides. Okay, so that's the case. And then let's go back to the linear acceleration. So initially, this is filled up with water. And now we accelerate, and we expect that the shape of the fluid will change. So the first question to ask is, what is the pressure at any arbitrary point inside the fluid? And then the second question is, what is the shape of the interface? So these are the two questions. Turns out that the answer is in these equations that we have. We can do it easily. Again, acceleration. So hopefully you understand the problem. Again, linear acceleration, the whole container is moving. The fluid particles, particle A and particle B, they are not moving relative to each other. So there is no velocity in here. Everything is steady state, okay? It's calm. Therefore, we say there's no velocity vector, but the whole system, the whole control volume is moving with an acceleration to the x direction. Okay. You guys still with me? Anybody say, make some sound? So.
Hello, sir.
Yeah.
Okay.
Here.
You're there. Wonderful. I'm really happy because I'm talking to myself and I don't know how many of you are there and how many are listening. So far, makes sense? Sounds reasonable?
Sounds reasonable.
Okay. Because as I said,
Reasonable.
now you really have to understand what I say. Last week, I did algebra, partial differential equations, and my intention was just to pictorial vision of you. But now you really have to understand. If you do an example, you should be able to solve it. Not going to be more difficult. It's going to be very simple, but still, just pay attention. Okay, thanks for responding, and I'm going to continue. Okay, so we go back to the same equation as had before. Okay, and remember the last equation. Okay, let me get the pen before it jumps on me. So this one, like it was before, this shows that the pressure to the y direction is not changing. And now there is a new term here. Okay. Minus rho A. We accelerate to the plus direction. And then the force is actually, the fluid appears to be the container accelerating, but the force due to acceleration is in the other direction. Okay. Minus. So then we integrate these three equations. So we end up minus rho A plus constant 1. Y direction, a constant 2 or 3, okay? And the Z direction, same story. So if I put everything together by combining and taking C1 and that constant, so these guys, adding everything together, we end up with this thing. So at this point, I'm starting to show you that it actually looks very much like I just keep the container fixed in the air and just tilt it. And then the fluid is going to stay level. But then in that frame of reference, and then we pick up a frame of reference like this, was a bit, this is X. Then it appears that there is acceleration here and acceleration. So it's very much the same thing. Why? Because we claim that gravity is an acceleration form. Because of the pull of the gravity, basically we have negative acceleration. Okay, so same story as before, but now we have an extra term, which is this one, this term. So let's keep on going. So remember, we just developed the equation, but now let's see if we can answer the question we raised before. So what were those questions? Question 1, what is the pressure inside the fluid? Any particular point. So boundary condition, let's take the previous one, and then we say at X, Y, Z, the pressure is 0. Pressure is equal to PA, which is the atmospheric. Plug it in the previous equation, so we end up with the constant is equal P. We move to the other side, so Px minus PA. Okay, the difference of the pressure because of the fluid is this, rho AX and GZ in that coordinate system. Remember, we picked the coordinate system, we picked the direction of acceleration. So, okay. Question 1 is answered. What is the pressure at X and Z based on this coordinate at any point inside the liquid? It is going to be minus rho AX and GZ. We have to pay attention that Z has to be probably negative in order to be inside the fluid. Okay, so what is the shape of the surface? I put a straight line here, but is it a straight line? I don't know. Let's see if it works. So what is the shape of the interface? We can claim that on the interface, the pressure, this formula here, the pressure is constant, PA, which is true. So this term is 0. Okay, the pressure difference is 0. And we still have these other terms. and then rearrange it to what is the z of that line, and it's going to be minus ax over gx, which means is the ratio between the accelerations. Or this is ax over g is alpha, is the tangent of the slope. So if ax is less than g, then alpha is less than 45. If ax is larger than g, then alpha is going to be larger than 45 degrees. Right? Very simple. So we were able to generate that. Okay, so let's do examples. Oh, before the examples. Let's see another trick here. The point I'm trying to make is that suppose you didn't go through all that integration and all that, you can still use the good old-fashioned rule that P of X equal rho GH. And what is H now? So if I go this point and I want to find out what is the pressure here, then I'm going to say what is H here, and therefore the pressure here, P minus PA is going to be equal to rho GH, which is the depth at that particular section. Okay, so let's see if it comes out of the equations we had. So first of all, we need to pick up an arbitrary point. So let's pick up an arbitrary point here. And then the coordinates of that arbitrary points is x1. Okay, x1. And then the depth at that point is h1. Okay, so this is how we picked up that particular point. Okay, so the surface z1, okay, so we want to find out how much is the depth of all that. So if I want to go to the basic formula, I'm going back. If I want to go back to this formula, because we claimed that this formula contains everything, then I have to put z. We said x equal x1, but I don't know how much is z. So we call z1, and z1 must be the depth in that coordinate system. So if I set up x, I said x, this is the point. This is x1. Then I need to say how much is z1 in that coordinate system. Okay? So let's see. Let's see if this is going to work. Okay, so z1 we're looking at is going to be minus axg and x1, which is this distance. Let me just not, okay, I touched it again. So this distance here is the surface, remember? So that is this one. That's the surface. And then we're adding another minus, which is h1. And now we did get z1, which is the depth or the location of point, this point in the coordinate system which we started with, this coordinate system. Okay? Now we go back to the old formula. So P of x minus PA equal rho do. So A1, X1 was given. Then G, and instead of G, it has to be Z1. We have to substitute this one here. Minus and do. And then if you solve that, G multiplied by that, these two terms cancel out. And then minus and minus goes away, rho GH. So that proves that in any condition, I can take a point. At that point, what is the pressure is going to be, if this is some H, let's say with an asterisk. So the pressure here P minus PA is going to be equal rho G H with an asterisk. Okay? Just very simple. So the simple formula does work everywhere. Okay, that was an easy example. I think I have some numerical ones. Okay. So let's do some numerical examples. So we have a case when the acceleration is such that the fluid, let me get the pen, the fluid is exactly leaving that point. So it's reaching the floor at the far end. Okay, we already know that this the surface is a straight line. So here's what's the question. Container is filled with water, it accelerates, and then the maximum liquid height in that condition is H0. And then the length of the container is little l. Again, that's little l. I see that the editor did a trick on me. The width to this direction. So if it goes that way, my drawing is not good. So the width is actually B of that thing, is this one. And what is the, calculate the acceleration, the total force Fz on the lower bottom horizontal surface and the center of the pressure. Okay, actually I made it more complicated than it sounds, but let's see if we can do that. So first of all, suppose the height is given H0 and the length is given. Then we have the shape of the surface is this, remember? I plug in the shape, okay? At this point, okay, so I push this point, minus H0 equal AX at L. So the coordinate X is L. I plug it in here, therefore I can calculate AX is equal to the ratio between the height and the length, okay? Which is now less than G, okay? Because the angle is less than 45. Okay, so that was pretty easy. And okay, so next, how much is the force on the lower surface? I can do the easy way and then the hard way. Okay, let's do the easy way. I know you guys are bored. The weight of the water is going to be equal H0 times L half times B and times rho. This is the volume. Anybody agrees? Anybody disagrees? I'm just doing high school stuff. That's the weight of the bottle. This is a triangle. Therefore, the weight is going to act at 1/3 of the distance. Any objections? High school people, you've been through high school? I don't hear a yes. Some people just start university from scratch.
Not this time, man.
I think I was in high school.
Yeah, you did go to
I kind of remember.
So you remember that
No,
stuff?
I just took the SAT only. No.
Oh yeah, okay, a smart guy. I love you. so this is it. Okay, so now, however, I'm trying to do here something else. I'm trying to do integral, because if this wasn't a straight line, then you would have run into problems. So I go here, is the force Z is equal the pressure times area. Okay, and I took out the minus because minus is acting down and so forth. Okay, so what is the pressure? It's rho GH, and then the width is B, and then dx is the length. okay? And then H is varying along this line. So we have to do an integral from 0 to L, okay? So need to figure out what is the shape of the curve. So the shape of the curve is equal to, when x is equal 0, it's equal to h0. And when x is equal to L, then 1 minus 1, it's going to be 0. So it looks like the shape of the curve is this formula. Okay? I plug the formula in, and okay, I have an algebra, simple algebra. Rho g h and b take outside, x minus x squared over 2L, integrate, I get this one. So what it is, let's see, b the rho g h0 b d, what did I say d? What is this d here? Oh, this is rho, okay, rho, all right, okay. Rho GH half and BL half. Okay, so one more time, I have a trick here. That's the computer that did that to me, here it worked. You see, rho G, that's it, rho G. It should be the same. Okay, so this is an error here. I don't know, the computer did a trick on me. Anyway, so it should be the same formula that we developed here. Okay, same thing. And then what is the center of the moment? So what we have to do is we have to come up with a moment equation about this point, the origin of the coordinate system. So the moment is force times x and dA. So the same formula. So rho gh of x, which is this one, x, and then b, which is the width, and dx. So we end up and this is the additional x. So now we end up, instead of x, we end up x squared half. And instead of x squared, we end up x to the third divided by 3L. Substitute L and 0, we end up over 6. And then the ratio is actually 1/3, because we say that the force, I call it W, let's say, which is equal to Fz. Statics, I'm doing the statics. So the moment, which we did here, is equal to the center of pressure, which is this thing, this distance, xCp, times the force. And then you solve it, you plug in the quantities, and you find out, you plug in this, and you end up, it's in 1/3. We said that before based on high school algebra, but this is very important. Now, center of pressure is also something super, super important. You have a ship, you want to know where is the center of pressure. You have an airplane, you want to know where is the center of pressure. So, okay, so let me just do this. So you have an airplane, and you have a wing. So you want to know where is the center of pressure, because gravity, let's say this is gravity pushing down, and now you want to know where is the center of pressure when it is lifting, which could be the same. And usually that's the situation when you have a pitch down moment. So how you make sure that it doesn't, you have some force which is actually doing this, pushing down a little bit, so balancing it. Okay, but enough of that stuff. Let's do one more. How are we doing time-wise? I have one more. Okay, let's do one more. Same thing. So the same container, same problem. Okay, so let's see what happens. We want to do some numbers right now, just algebra, see how this works out. So if the maximum liquid height is 0.2 meter here on the left-hand side, let me get the pen. From here, this is 0.2. And then the length is 0.8. Yeah, it's definitely playing with me. The width, B, is 0.4 meter. How much is the acceleration? So the previous example, we had it exactly the same. So here's that water density. So the ratio between the two lengths is actually 4, therefore 0.2, 0.8, which is the two length. The acceleration is quarter g. What is the force Fx on the left side? What is the force on the left side? Basically, it's MAX. Okay. So what you can do is you can do the same algebra as before, which is rho AX and then the volume, okay? And it's 1,025.25 G, and then multiply the length ratio, which is quantity in the G, the height, and then the width, and you end up with 78 Newton. Center of pressure, remember Z is, the coordinate is actually here. So the center of pressure is going to be 2/3, somewhere here. Okay, so I'm just using the previous integration results, which are very much the same. Okay, very much the same. And this is that one. So then, so just putting numbers in it. And then again, the acceleration, which we mentioned before, is related to the two forces, which is logical. So that was a very, very simple example. By the way, this was one of the exams, I believe, 10 years ago or something like that. So if you have a problem like that given to you, you should be able to solve that. We have a few more minutes, so let me just introduce the next one. We mentioned that we're going to do acceleration, fluid acceleration, in two cases. The first case was the linear acceleration when the container with the fish is running from one side to the other. A much more easier case to demonstrate is we're having a circular container, okay, a circular container, and then we're just simply spinning it. So one more time, artistically, we have a circular container. And then we're putting a coordinate system here. So this would be the radius R direction, and this would be the Z direction. Okay, so this is what we're doing. And then we're spinning the container, and then the liquid will assume some kind of shape, which appears to be a parabola or whatever, this shape. And of course, again, the fluid particles, particle 1, particle B, C, and they're not moving relative to each other. The fluid is basically stationary. And then the two questions, why did it go away? The two questions we asked before is, okay, what is the pressure at any point here? If I take a point here, what is the pressure? And then the depth is going to be, say, H. Question 1. Or anywhere, any point, what is the pressure inside the fluid? And what is the shape of the interface? These are the two questions we're going to ask. And then we're going to do some examples. So we take a fluid. We take the fluid. And we probably fill it up here. This is all fluid. And then we spin it at the rate of omega. And then we end up with a shape like that. So then we're going to ask those questions. And we go back to the same formula that we had before. So what is the body force? Okay, the body force is minus G, as we called it before. But now we said the acceleration is the acceleration because of the fluid. So it tried to go to the minus, we're forcing the particles to accelerate inward because the wall of the container is pushing the fluid inward. Otherwise, it would spill. So the acceleration to the radial direction is r omega squared, which you of course know. And then we have to write down the equations in the cylindrical coordinate system, but it's very much the same thing. I think we're running out of time, and we'll do that next time, but it's going to be very, very similar, a little bit more complicated than the linear acceleration because of the coordinate system. And okay, so let me do just this for a second. What is that? Yeah, that's what I wanted to see. Okay, any questions?
Professor, can we look at the second triangle example of the tank? That one. For the acceleration in the x direction, I'm not following exactly how we're getting that 0.25 g. I see the...
This one, we did that, and then the acceleration to the x direction is, this is the formula.
And why is it h naught over L times g? Why is it proportional to g again?
Okay, so let me go full screen. Let me get the pen. Okay, so the shape of the surface, this surface, is this, right?
Mm-hmm.
We developed that formula before. Correct?
Right.
And then I just substitute a point on the surface. I pick that point, okay? Where x is equal L, and h is equal that one, and g is g. And therefore, I conclude that the ratio between the acceleration is this. And this is when I mentioned the story about alpha, about the angle of the surface versus that, which is going to be less than 45 if the ratio of the length to the height of the floor. Now, of course, if it doesn't have to be this way. If say it's a different container, you still have the surface shape, and it's still the same formula. Okay, so then I go back. So if you agree to that one, then I go here. Oh, same equation. So here's the formula. Oops. Okay.
Yes, thank you.
That's it. More questions? I think this is simple. You have to just follow through. I will post the lecture later on, and then hopefully between these two things, and you have it recorded as well, and you can always go back an hour, 15 minutes to listen to. I wouldn't listen to that twice. Okay, class. Thank you very much, and see you Thursday. Okay.
Thank you, Professor.